Hello and welcome to this video. So in this video, we want to start talking about the modeling of systems. And I want to start the discourse by making use of a simple electrical network. I think I'll use an RC network with a resistor and a capacitor. A single resistor is single capacitor. Let's say this is our voltage source. Let's call it V of S. It's a time function. This is a resistor. Let us simply say it has a value R and our capacitor has a value C. Let's say there's a current flowing in this direction, I of t. And let's just put a reference node here, even though we don't necessarily need to write that. So this is our system. We want to work with this system. To create a mathematical model of this system, we use a known law. So let's use the KVL, that's the Kirchhoff's voltage law. Using Kirchhoff's voltage law, we know that the sum of voltages in any loop gives us 0. So that we have, if we know this is the current flowing in this system, and let's just simply say that the voltage across the capacitor will represent that as Vc. Then we could have that our Vs of t. Now, because the current is flowing in this direction and we're going in this direction, the current that will be the voltage potential drop across the resistor will be negative. So that will be against, since it's a sink, it's not a source, will be against our movement. So that is I minus I of t times R. And then again, same thing with the capacitor, because we're again going against the motion and it's a sink, not a source, then we will have this as being negative of Vc. I'll just simply write that as Vc of t, being the voltage across the capacitor. So we could say that the voltage across the capacitor plus and a minus Vc of t, and the voltage across the resistor will be also in the same direction, V of R, where V of R will simply be IR. So sum of these is equal to 0. Sum of these is equal to 0. Okay, let's go one step further. Now the current in this circle in this circuit at any point in time, or if you want, the current in the capacitor at any point in time. Now, because it's a single loop in the circuit, the current in the capacitor is the same as the current in the circuit. So the current in the capacitor at any point in time is defined as C and the differential, C multiplied by the differential, the Vc dt. Okay, C multiplied by the differential of Vc. So let's slot this into this expression so that now we just have two parameters. You have Vs, Vs of t minus Rc multiplied by the Vc dt minus Vc of t is equal to 0. And this is a mathematical model. This is a differential equation model of this circuit. The differential equation model of this circuit. In this system, I'm taking the output of this circuit to be Vc. So if you want, we could connect our outputs over here, and we could say we're interested in this potential difference here. We could call it our VL if we want, but VL in this case is the same thing as Vc. VL standing for V load, but let me leave it as Vc so that it's not confusing at all. So this is Vc. This looks like an R. So no, still looks like an R. If I can write, then we'll take this as Vc. Okay, so Vc of t is our output and is the same as the potential across the capacitor. I'm sorry, my writing is just all over the place. Yeah, so we have this. Now, based on what we know so far in this course, let's go ahead and take the Laplace transform of this function, of this equation over here. Take Laplace transform of this equation. We have V of s, so that's Vs of s, Laplace transform of Vs, minus Rc is a constant, so it stays out there. You have a differential here. The Laplace transform of a differential is s multiplied by the item. So you have s Vc of s minus differential of this is simply Vc of s. Now I'm using upper cases, is equal to 0. Now I'll take the Vc terms to the right hand side and collect. Oh, I've left something out. This is a differential, so let me take this off also so that we are clear. So we had a negative sign here. Let me keep that and put in parentheses. And we need to remember, this remains there. This is a differential. Sorry, this is a differential over here. So we have our initial conditions. So RC multiplied by VC initial. Okay, I'll close that up now, and then minus VC of S, all being equal to 0. I'll take the VC terms to the right hand side and collect like terms. So that means that our VS of S is equal to, let's say, VC of S into SRC plus 1. Then I'll have a minus RC VC initial condition. Okay, so I hope you can see what I did here. You have your RCS CV, that comes out SRC over here. Then you had your VC of S, that's plus 1. Then your initial condition goes out there. Okay, and so this is what we have in the Laplace domain. But this is not very helpful to us unless our VC of 0 is equal to 0. So assuming 0 initial conditions, if we have 0 initial conditions, then this will cross to 0. So let me write assume here, because this is not always the case. But if we assume 0 initial conditions, then this goes to 0. And then we now have a simple circuit where we can simply say, we have a simple equation rather, where we can now say, we set our output. If you remember, we're making the output of our system VC. Okay, so if the output of our system is VC and the input of the system is VS, then we can now write our equation for the system as output VC of S divided by input Vs of S, and that is equal to, so now you have 1 divided by SRC plus 1. Okay, 1 divided by SRC plus 1. This is called the transfer function. So this is the transfer function of this system. Now, this is not the only possible transfer function we could have, but based on our assumption, or based on the particular input and output we chose, then the input-output characteristics of, or the output-input characteristics, the input-output characteristics of this system, based on the fact that Vs is our input and Vc is our output, is 1 over SRC plus 1. So this is our transfer function of the system. Now, take note that this transfer function assumes 0 initial conditions. So to find the transfer function of the system, to arrive at the the transfer function model of a system, we have to assume that there are 0 initial conditions. So 2 more things I want to mention about this particular transfer function. First of all, this is a first order system. So this transfer function tells us it's a first order system. Now we know it's a first order system because your denominator has only the highest power of S in the denominator is 1. So this is a first order system because the highest order of S in your denominator is 1. So it's a first order system. We know that. Secondly, in many cases, we often tend to write this expression as 1 over RC over S plus 1 over RC. We could choose to write it this way. All I've done is divide each term by RC. So we could write it this way, we could write it this way. It is perfectly fine, whichever way you choose to write it. The reason why I state this is some prefer to write it in this form. And your RC, by the way, is called your time constant. And you know that already. You know this already from electronic engineering. Your RC is simply called the time constant of this particular system. If you remember this system really is called a low-pass filter. But then we don't need that information right now. All we're doing is just modeling this system. And your RC is called the time constant of this particular system. So we know that usually we represent time constant by the Greek alphabet tau. So in other words, we could have written this as 1 over S thou plus 1, or we could have written it as 1 over thou into S plus 1 over thou. Now, I'll say, depending on your preference, write it in whichever way, depending on your preference, but this is for this particular system, and it's just interesting to look at it this way. Now, the way we draw this as a block diagram, we could draw this as a block diagram. Since we have the transfer function, I'll use this first expression. Since we have the transfer function as 1 over SRC plus 1, we draw that in a block. And to this block, you have two arrows, one coming in, typically on the left, and then one going out, typically on the right. Now, you could have inputs anywhere and outputs anywhere, but typically, if it's in a forward path, we just tend to draw it this way. Your input to this system is Vs of S. Output from this system, Vc of S. So this is typically the way we draw it. And this is a block diagram representation of this system. So what we have done in this short video is we've come up with 4 different representations, or 3 different representations of this system, or let's say 4. The first representation is this schematic, an electronic schematic diagram. Okay, so that's the first representation. Second representation we have, so let's label this as 1. Let me use a different color so that it kind of pops on the screen. So this is the first representation of the system. The second representation of the system is what you have as the differential equation model of the system. So that's the second representation of the system. Now, the third representation of the system is your transfer function. Okay, the transfer function model of the system. That's the third representation. And the fourth representation is this system here. Now, obviously, the third and the fourth representations are related because they are a transfer function. Transfer function is used in the block diagram. The first and the second also, you could say, are related because they work in, both show the system in the time domain. But then there are different ways of representing the same system. Each of them represent this same system. And yeah, that's that. Now, remember in this system, we chose Vc as our output and Vs was our input. What if we had said that, no, the current flowing through was our output instead? We could have chosen to say that the current flowing through was our output instead. Now, if that was the case, then let's come up with the, so I'll do this in, let me go back to my normal orange. So if that was the case, maybe I should just redraw the circuit over here. Can I copy what's up there? Would that be convenient? Yes, I can copy what's up here, I think. Well, no, let's just redraw it and save ourselves any unnecessary time to clean up the diagram. So we have a circuit with a resistor on the top, a capacitor over here. I apologize, this is not the neatest of diagrams, but I really do not want to take too much time drawing something that is really perfect, and it's not actually easy to draw on a computer. So let's say that our output is our I, and then this is our Vs of t at the inputs. Again, our plus, our minus, and plus minus, plus minus. This is our Vc, this is our Vr. Okay, so this is our system. Differential equation model, first place to start from. So we have our Vs of t, subtract our I times R, subtract our Vc is equal to 0. Now, what do we know of Vc? Vc is given as the integral, actually from 0 to t, of 1 over c multiplied by the integral of I dt. This is our Vc. So we can slot that in here. And we have our Vs of t minus IR minus 1 over c, 1 over c, integral from 0 to t of I dt is equal to 0. Once again, we take the Laplace transform of this system. We have Vs of s minus Ri of s minus 1 over c. Now remember, integral of this, you have an s in your denominator now, 1 over sc I, 1 over sc I of s being equal to 0. Okay, so we have this expression. We want to take all the i's to one side and keep the, because remember all we want is output over input. So we have Vs of S is equal to, let's collect like terms, I of S into R plus 1 over SC. Okay, and so output over input, output is current. You have your I of S over V of S, Vs of S is equal to I divided by V. So V comes down, this goes underneath. You have 1 all over R plus 1 over SC. Let's simplify this a little bit. It's the same thing as you could have SC coming up and you have SRC plus 1. I believe this is correct. Let's just see. So we have SRC plus 1 over SCS. So this is what you have as your expression. And now this is your transfer function if the current is out. So if let's draw the block diagram for this system. That's, excuse me, SC over SRC plus 1. Put this inside a block. It has an input, it has an output. What is the input to this system? Vs of S. What's the output from this system? I of S. Okay, note that this is I of S. I is the output of the system. Okay, so this is another model of the system. We're at 16 minutes, so this is where we're supposed to stop. But just one thing to take note of. If the current is I of S, okay? If your current is I of S, what's the relationship between VC and the current? I think we wrote that somewhere. Where did we write that? Yes, we said I is equal to C dV dt. Okay, C dV dt. Let's, if you don't mind, let's just take this expression. Let me actually copy this expression. I'm sorry, I'm going a little longer than I like to go in videos, but then I should stop in about 1 minute. So let's say we took that expression that we just did, and let's find the Laplace transform of this expression. So the Laplace transform of this expression now goes and become I of S is equal to SC VC of S. And this, by the way, is assuming zero initial conditions. If we assume zero initial conditions, we can leave out the initial conditions. So I of S is simply equal to this. And we could say that VC of S is equal to I of S divided by SC. Now, the reason why I'm saying this is VC is equal to this. So if my input is I of S and my output is VC, then output over input, VC of S divided by I of S gives us 1 over SC. So what we have just said here is that if we had a system that has, if we had a block diagram, or if you had a block that had an input of I of S and the output was VC of S, the transfer function is 1 over SC. But hey, we actually already do have something. We have an I of S somewhere. So can we put these two block diagrams together? Let's put these two block diagrams together, and what we get is, if we had our, I said I'll stop in 1 minute, so I'm trying to rush to make sure I finish this. We have SC over SRC plus 1, and your input to this rather is VS of S. So Vs of S, and the output of that is I of S. But the output of that I of S goes into another block, and that other block has a transfer function 1 over SC. Output of that is VC of S. And this actually is perfect mathematics, and this actually works perfectly out. So let me jump ahead of us a little bit. With block diagram reduction, all you do is multiply these two terms together to reduce this into a single block. So if you wanted to reduce this into a single block, this now becomes a single block here, where you have SC over SRC plus 1 multiplied by 1 over SC. Output of this, VC of S. Input to this, Vs of S. And this is obviously equal to a single block. with a transfer function 1 over SRC plus 1, output being VC of S and input being VS of S. So this I'm just doing to show that you have, it's an equivalent system. Whether you represent it as a differential equation, as a block diagram, as a transfer function, as a schematic, this is all one and the self-same system. Now that we specified I as our output, there is another transfer function we can get to take this output I and take it into and change the output, for instance, to a VC. Okay, so it's just by multiplying this, what we had before, by a new transfer function, or taking the output previously into a new system with a new transfer function, we get another a different output of the system. So I do apologize, this video is a little longer than I thought it would be, but I hope you've learned something. In the next video, I think we'll take up, let me just leave that to the next video. Okay, so see you in the next video.